So the problem is, of course, life is rarely ideal, especially when you go into nursing. You get lots of things that are not ideal. And if there's a net force, if that net difference is between 1 and 3, 1 and 2, the lymph system, which was another lecture, you'll see it up, will absorb the difference. But if it's more than that 2 or 3, we do have this net filtration. So even if it's between 1 and 3, there is net filtration. The lymph system will pick up most of it. But if we exceed that ability, we will have edema, which is also called swelling. And people who have this net filtration, they'll actually have swollen fingers, swollen toes. They may have a swollen face. Where we really don't want swelling is in the lungs. But if the net force is less than 0, if we have a negative number, -1, -3, it means that there's net reabsorption of water into the tissue, from the tissues into the capillary. So water is moving, more water is moving into the capillary. We usually see this in cases of blood volume, where we have dehydration or hemorrhage and we need to restore blood volume. So any negative number always means reabsorption. So we do have some exceptions. The lungs should always have a net force of negative. We should always have reabsorption. Okay, it should always be reabsorption. And this keeps water from building up in the lungs, and it keeps us from having excess fluid in the lungs, which would be congestive failure. This is not a sign of dehydration, it is normal. On the other hand, the net force in the kidneys is always positive, because this force in the kidneys, this net filtration in the kidneys is what leads to urine formation. Now, there is another document in this folder, in this unit, that says Starling Forces example problems. And I highly encourage you to work your way through those example problems. I've done them for you, but you can see them, and they are part of my board drawings. So I'm going to do this one, but there are more examples later. If a patient is suffering from dehydration, their hydrostatic pressure might fall to 31. Remember, normal was 35. So that means their lack of blood volume, they're dehydrated, makes their blood pressure fall. And that means the venous pressure will also fall. Maybe it goes down to 12 instead of 15. But the oncotic pressure will rise slightly due to the lack of water. So maybe the OPV is now 30. And the tissue hydrostatic pressure doesn't change, and the oncotic pressure doesn't either. So it's the blood that's changing due to this dehydration. So when you are solving these problems, the first thing you want to do is set up your H. I call it the H. It's the arterial with the crossbar, that's the capillary, and then the second part is the venous system. Set this up, put your numbers in your capillary drawing. We have HPV of 31, we have the oncotic pressure of 30, we have the HPV at the venous end of 12, and we have the hydrostatic pressure and the oncotic pressure of normal. The other thing I encourage you to do is color code. You notice how my tissues are green, my arterial end is red, my venous end is blue. It's okay to color code. In fact, it's encouraged. So then when we solve it, here's the equation. And on the test, yes, this will be on the test because it's math, I will give you the equation. What I expect you to be able to do is solve it. But remember, you have to solve it twice. So the arterial end, remember your parentheses, was 31 minus 0 minus the 30 minus 3. And therefore, we had 31 minus 7. We still have some filtration, but 4 is much lower than 10. The venous end, we had the 12 minus the same. Remember, the oncotic pressure doesn't change. And we get minus 15, much more negative than the minus 10. And then when we solve for the net, remember this one's plus, right? We get positive 4 plus a negative 15 gives you negative 11. That means that there is net reabsorption. Water is moving from the tissues, from the ECF, and into. So it's from the ECF, the extracellular fluid around the tissues, into the capillary, and it will restore the blood volume at least partially due to the dehydration. If I did a hypertension example, I would say that the hydrostatic pressure in the arterial end may go up to 40. That's higher than normal. The oncotic pressure, in this case, I'm keeping it the same, although it can change. And the hydrostatic pressure at the venous end also goes up. But because of the hypertension, my hydrostatic pressure here in the tissues change. So you're going to have a word problem like this. And then what you're going to do is build your capillary with your values, set it up so that you can read 40 at the capillary end or the arterial end, 13 at the venous end. Actually, wait a minute. Did I do that right? That should have been 18, not a 13. So this should be an 18. Hopefully I did the numbers right. And you can see where I've put in those. So arterial end, positive 13, I did put the 18 here. So it was only in my H that I miswrote. But we have to make sure we have everything set up. So the arterial end, and then we did our PEMDAS first. We see that now we're plus 13 for filtration. Remember, normal was 10. So we have a higher than normal filtration. And we do the math, and we see we're at minus 9, which is a lower reabsorption of only minus 9 instead of minus 10. So we solve the math and we say arterial plus venous. Hey, look, we're at positive 4. That's higher than my plus 2 or plus. So we are going to see in this person edema, which is also called swelling in the tissues. Their fingers might be swollen, their feet might be swollen, which is very common in hypertension. So you will have the word problem, you're going to build your capillary, and then you are going to do the math. I will give you the equation, but you have to do the math.